What I want to do today are two examples, slightly complex, one with no real answer, but some ideas as to how to solve it, but to give you an idea of what to expect in terms of general plane motion and the approach taking. And one of the things I strongly want to stress here is that it's really important to understand how free body diagrams work. And so the goal here is really to take some of the ideas from kinetics, chapter 17 in Hibbler, try to give you some more insight into the analysis, and to try and get you to sort of do some more things looking at these problems. And what I want to do is, first of all, a relatively simple problem, well, kind of simple, and look at what I do on a weekend. So on a weekend I have nothing better to do than push a lawn roller. So a lawn roller is a device with a very heavy weight on it and a handle. So the mass of the roller is 103 kilograms, mass of the handle is 6 kilograms. Rho equals 243 millimeters, L is 1.2 millimeters. I maintain an angle of theta of 35 degrees, and the center of that roller is going to accelerate at 0.47 meters per second squared. And you're asked to find two things: the force at A I must apply in order for the handle to achieve this motion, and the minimum coefficient of static friction between the roller and the ground if the roller is to roll without slip. I'll do that well. And what you're trying to do, you've got to kind of recognize, treat the roller as a uniform circular cylinder and the handle as a thin rod. And so you'll remember from the early parts of this chapter, we talked about circular cylinders and thin rods already. So there's my handle, there's my coordinate system, and you should always write your coordinate system. Those are my two lengths, and that's my weight. So that's the handle. Maybe I should write hand. I don't believe I wrote handle on this. And those are my two reaction forces, AX, AY, BY, BX. All right. So my next thing is to look at the spool, or the lawn roller itself. It has a radius of rho, and I have the corresponding BX and BY. I also have force of friction and the normal force. I kind of expect that this is rolling in this direction. And if I do that, I got all of this stuff. I'm kind of working through it. I want to sort of point out one thing, which is that I've reversed the directions on the two forces because of Newton's third law. So if I brought the roller and the handle together, then those two forces would cancel out because they are an internal force in the system. But because I've split this system apart, I have two forces and they have to be equal, opposite, collinear, and so cancel out when I do this. So if I look at the handle, the mass of the handle is here, L squared 1/12. You know this already, or you should sort of imprint this in your minds, that a long slender rod is 1/12 ml squared. I have AX, which is in the positive direction. I have BX, which is in the positive direction. I have mass of the handle times AGX. I also have AY, which is acting upwards. I have BY, which is acting upwards, and I have weight, which is acting downwards. And so MHAGY. Then I have to look at the two forces. So BX is causing a counterclockwise force, which is positive. AX is causing a clockwise rotation, which is negative, BX minus AX, L over 2 sine theta. Same thing for BY and AY. AY tries to cause a clockwise moment, and BY tries to cause a counterclockwise moment. So that's positive minus negative, and this is IG alpha AB. And I know what IG is already because I've already calculated, or I know it from definition. On the roller, I have the forces here, and I should have my X, Y, which I do actually, right there, X, Y, and I have a coordinate system that is counterclockwise. So BX minus F, force of friction, and force of friction over here. So BX minus FF, mass of the roller, and ABX. N, the normal force, minus By, minus mRg. All of these two forces are acting downwards. Mr times ABy. Finally, I have the moment. The only thing that's causing a moment about point B, which is the center of mass, is frictional force, minus FF rho, the radius, IB alpha r. And IB for a cylinder is 1/2 mr squared. Again, this is something that as you're going through the moments of inertia, you really got to remember some of these, and this is another one that's kind of important. So in terms of force laws, we kind of assume that the force of friction has to be less than or equal to mu sub s times n. That's great. That's for rolling without slip. Since theta is constant, omega AB, alpha AB is equal to 0, and AG equals AB. So this is a translational problem. Now, and this is the theta we're referring to here. ABY is acting downwards, and that's 0 because this thing doesn't bounce. And alpha r is just going to be roll without slip, so it's going to be the acceleration of bx divided by the radius. And it's negative because of the cross product rule. So if I put in all the terms, I have ax plus bx, mh abx, ay plus by minus mhg equals 0, L over 2 times all of these terms, and I can start substituting in terms, combining things. And I have 6 equations with 6 unknowns: acceleration x, acceleration y, bx, by, force of friction, and normal. So I have enough here to solve through, and I can start substituting in terms. So ax, if I substitute in, is going to be 75.4 newtons. Ay is going to be minus 22.4 newtons. Kind of makes sense. I'm pushing down on the roller to sort of hold it in place, and I'm pushing forward to get things moving. Bx and by, minus 72.6 newtons, kind of pushing against me. By, 81.2 newtons, which is, again, kind of, heavy roller. Force of friction is 24.2 newtons, and the normal force, after all of this calculation, is 1092 newtons. So that force that has to be applied is 75.4 newtons for the x term, and 22.4 newtons for the j term. So my total total force on A is given this way. I could have written it a number of different ways, and I'll talk about one of those other ways in a second. Minimum coefficient of friction has to be less than the static friction, and that is a very small number in this case, 0.022 newton, or 0.022 no units. Now, if I have done all of this and everything has worked out very well, I can start to look more closely at what's happening at the surface. And I jumped the gun a little bit. But my AY, AX look like this, and my BY, BX look like this. And if I just do the trigonometry or the geometry, I get the A is acting at 16.94 newtons down from the vertical. If I look at B, I'd have to sort of recognize it sort of goes all the way over here, but that's 138.2 degrees to that point. Now, one of the questions is, these forces are not parallel to AB, and unfortunately I forgot my animations here. Why? The weight of the handle is included. And also, center of mass of this handle is accelerating. It's a translating problem. Well, let's look at a more complex problem. This is a problem that I just want to sort of throw out there, and I kind of would like to leave this as a problem that you could try on your own and sort of think about later. But this is a problem that I can put on a final exam or on a midterm, and I can guarantee it will drive everyone crazy. Thin rod is suspended from the end of a spring, suspended from the ceiling. We let the rod swing. What are the equations of motion for a system like this? Okay, and that might be the problem that I ask in the final. It gets a little bit more involved, and I mean, the big thing is that the motion is very complex. But really, this is not that bad when you start to draw the free body diagrams. So you have force of the spring out here. So that's, again, you've got the spring and you got this, like this. And this is at phi, and this one is at theta. And I did a better job sort of showing some differences between the two. You see that the only forces acting in this system are force of the spring on one end and weight acting on the other. I need to know phi and I need to know theta. That's about it. So I also want to define a coordinate system. So I'll define a coordinate system that is r theta for the force of the spring and xy, which is for the long slender rod. Now, if I do that, I have a force in x, which is just going to be the force of the spring. And the force of the spring is just going to be minus fs sine theta, because that's the only term that plays a role in the x direction. I have weight, which is acting downwards, and force of the spring, which is acting upwards. Again, I want it in this xy coordinate system. I didn't draw very well, but it's mg minus fs cos theta, which equals ma gy. Then the only thing I need to know is what the moments about g are, and the only thing that's causing moments about g are going to be r, the distance from here to here, a with respect to g, crossed with the force of the spring as a vector term. And that's going to equal Ig alpha AB in the k direction, and I need to sort of fix that. Again, Ig for this is 1/12 ml squared. Force and position vectors are described in terms of either coordinate, but L over 2 minus sine theta, sine phi I plus minus cos phi j. It's hard to even say it. And force of the spring is given as minus sine theta I and cos theta j. So I have to break this down, and that's where some of the complexity comes in, recognizing that you've got two coordinate systems and you got to bring everything together, and then finally putting everything together so that you end up with the correct terms. And so you end up with 1/2 L fs sine phi minus theta equals Ig alpha AB. This is a problem that, again, as much as possible, try it on your own. Try to do these, try to get comfortable with some of these ideas. Force of the spring is then given as r minus r naught, and r naught is just the unstretched length of the spring. You have the kinematic expressions, which is Ag equals AA plus Ag with respect to A, which is here it's ATG with respect to A in the, ATG with respect to A, ANG with respect to A. Putting in all the terms and recognizing that certain things are not going to change. For example, R doesn't change between G and A, so its alpha AB is only going to depend on theta or phi double dot, and so minus phi double dot K. And omega is also doesn't change with R, and so it's going to be phi dot, and so you end up with Rg with respect to A, which is equal to negative Ra with respect to G, which is L over 2 sine theta or sine phi I plus cos theta J. So after you have that and you have the UR, the acceleration in A, you can say put it in terms of UR U theta. You can recognize that UR is going to be a sum of X and Y components and X and Y components. They're normal to each other, they still have to be, but those X and Y then flip signs. So sine theta plus cos theta, sine theta I, cos theta J, and maybe I want to do this here, moving forward. And I get as a final result this nightmare. And it's not, and I'm being a bit facetious here. It's a nightmare because it's a lot of work to go through, but I have AGX in terms of r double dot r theta dots squared sine theta r theta double dot twice r dot theta dot cos theta plus L over 2 phi double dot cos phi minus L over 2 phi dot squared sine phi. Now that's for AGX. I get the same sort of relationship for AGY with some signs flipped. Now that sounds terrible. It's a little bit terrible, but it's actually kind of exciting that you can get all of this with in a relatively painless way. So you can substitute these into the equations in and sort of work everything through, and you'll get 3 equations that really can only be solved by computer. Okay, that's fair. So you got everything in terms of r theta dot r double dot r dot r theta dot r double dot theta dot theta double dot phi dot phi double dot, etc., etc., all the way through all of the terms that you've solved through. And despite the fact that, yeah, I recognize this is a pain in the neck in terms of writing these equations, this is actually not too bad. You've got a lot of complex information. This is a very complex motion, and it's a complex motion that you can solve using relatively simple ideas and simple geometry. So you need to sort of think about how you're using these simple geometries as you go through this. And you should sort of check things, but the equation that has units of acceleration, you can check later. And if you want to try this, here's a couple sort of initial conditions that you can try to solve through and work through the expressions. And I think that's all I really want to say about it. Just recognize that those are your 3 unknowns, and you'll figure some stuff out as you go through this. But you really need the help of a computer. This is something that, as much as possible, and certainly I recognize you have a lot of stuff on your plate, but it's really useful to sort of start to think about why we've been programming things for now pretty much on 60 years, and how can I use this for my own courses. And I'm trying to push that a little bit more year by year in dynamics. Again, this is really kind of, the last one particularly is a very complex problem. And again, I may have been a bit facile with my comment about final exams and that particular second problem. First problem, no, that's a problem that is relatively straightforward, and I think you should be able to handle that sort of level of complexity. However, the second problem is interesting from starting the idea that you guys can do a lot of very complex computational modeling, and the results are kind of fascinating if you run it, just to get a sense of what's there. It's something I kind of recommend, and I hope you'll give it a shot. Thank you very much, and we'll talk again.